graph, if I just give you the function, can you find a limit with just algebra, meaning mechanical manipulation? So that's basically what I say there. We now discover a way to calculate limits by analyzing the function itself. This will require significant amounts of algebraic skill and tricks. So this is where you start to run into the true issue of calculus. And, you know, this is just the way it is. The concepts of calculus are usually not difficult for students to understand, the idea of what we're trying to achieve. It's usually the algebra that's involved that causes the problems. It's the complexity of the algebra that can make students struggle with the course, right? So we're about to start to see some of that. There's a lot of things you need to know how to do. So first thing we're going to do is we're going to establish what are called the limit laws. These are things that you are allowed to do. Yeah. These are things that you are allowed to do when it comes to doing limits. You can do these without question. These are truths that have been proven. We're not going to prove them, all right? This is not a theorem proving course. Now, when I show this to you initially, it's going to look like crazy, all right? So just let me talk through it first, and then we'll start doing examples. The first limit law says that if you're ever trying to find the limit as x approaches some value, and you have two different functions that are added together, you're allowed to look at the limits of each one of them separately. So you can just focus on one of them, figure out that limit, find the other limit, and then add the two answers together. So the way we say this is the limit of a sum is equal to the sum of the limits. The two limits take their sum. Same thing goes for the difference. If you have subtraction between two functions, you're allowed to take a look at each limit individually and then subtract them. The next limit law says that if you have a limit of a function and then you have a number, C here is a constant. So you have a number sitting in front of the function. What you can do is ignore that number, bring it out front, take the limit of the function, whatever that answer is, multiply it times that number and be done. So constants can be factored out, is what that says. This next one is a beautiful law because it works the way that you would hope it would work. And that is if you have multiplication of two functions and you're trying to find the limit, that you can find the limit of each one and then multiply the two answers. That is actually very nice that it works that way. Division works the same way. That if you have a limit and you have a quotient of two things, two functions, one on top of the other, that you are allowed to do the limit of the top and bottom separately and then get that answer. The only problem you could ever have is maybe if this bottom one goes to 0. If the bottom one goes to 0, then you can't do it. So that's why there's that little condition here on the side that this only works if the bottom doesn't go to 0. The sixth limit law says that if you're trying to take the limit of a function raised to a power, what you can do is you can go look at the limit of the function first, figure out what that answer is, and then raise that answer to that power. So it's like you can go inside the power, do your limit, and then just raise it to that power when you're done. Again, don't get bogged down on all this. I mean, we're going to do examples, all right? There are 72 limit laws. No, I'm kidding. We're almost done. We're almost done. Number 7. You have to memorize them by the end of class. Limit as x approaches a of a constant is always equal to a constant. Let me show you that as a specific example. If I say this, hey everyone, what happens if I let x approach 2 of the number 5? It'd be 5. Because do you see there's no x's here? So if I say, hey, let x go to 2 and tell me what happens to 5, well, nothing happens to 5 because x isn't here, right? So this is just going to be 5. 5 stays as 5. That's what that limit law is saying. The next one, however, this law says that if you let take the limit as x approaches, let's say 2 of x, right? The limit as x approaches a of x, then I'm saying, hey everyone, what happens to x when x goes to 2? It goes to 2, right? It's almost so obvious it's tricky, right? Let x go to 2. What does x go to? 2. Okay, that's what that law says. And then I can do this one here. This one says, if I said, hey, what's the limit as x approaches 2 of x to the third power? Well, let x become 2. What does this become? 2 to the third power, right? Which is 8. That's what this law says. If x approaches a of x to the n, all you're going to do is replace that x with a, and you're done. Let me put these up here. 10th limit law says if you take the limit as x goes to a of the square root of x, all you're going to do is replace that x with a. And our last limit law says that as long as, when you're taking a root, as long as that root is even, then, well, I should say it this way first. Hold on. If you're taking the limit as x goes to a of the nth root of a function, you can take the limit inside, figure out what this limit is first, and then take the nth root. So you're allowed to move the limit underneath the radical sign first. We do have to be careful though, because if this limit turns out to be a negative number, and that n is even, we can't do the even root of a negative number. That requires imaginary numbers, and we don't deal with imaginary numbers, all right? Ever, until you get past Cal 3. You actually have to get past differential equations in Cal 3, then you can take a class called complex variables where you actually deal with imaginary numbers. There's a reason why, I might get into it later. There's a reason why we don't deal with them here. All right, so given those limit laws that are probably just really sketchy in your mind right now because we haven't really done any true examples, we have this extremely important property called the direct substitution property. And I have some preliminary stuff to talk about before we actually do it. So before we discuss the direct substitution property, we all need to understand something called an implied domain. So if somebody hands you a function, says, hey, take a look at this function. When you're looking at that function algebraically, there's an implied domain, meaning there's, just by looking at it, you should be able to tell what values of x can and cannot be plugged into the function. So look at this function right here. I'm going to do this, let's do it on the side. I'll do it right here. So if I look at this function right here, if I just hand this to you right now and just say, hey everyone, look at that function. You should all be able to look at that, do a little bit of thinking, maybe some work on the side, and figure out what its implied domain is. So when I look at that, the first thing I notice is that the denominator here can't be 0, right? If I have 0 down there, it's bad, right? So I know right away x cannot be what? 4, or else I have division by 0. So x can't be 4 for sure. And then the other issue I have is that this is a square root, and I can't have a negative under there, can I? No. So that means that x has to be positive, or could x be 0? What's the square root of 0? 0. So you can take the square root of 0, you just can't do the square root of a negative. So not only do I need that x not be 4, I also need that x has to be greater than or equal to 0, right? Both of these conditions have to be met in order for that function to be defined. Which means the domain, written in set notation, is x is any real number. That's what this means. X is an element of the real numbers. So it's just x is some number such that it has to be greater than or equal to 0 and it cannot be 4. If you wanted to look at that on a number line, what we're saying is this. If this is 0 and this is 4, we are allowed to plug in 0. Anything to the right of 0, we can't plug in 4, but we can plug in anything past 4. That's the implied domain of this function. which means if I graph that, if I go to Desmos and I graph that, we should only see the picture existing from 0 to the right, and at 4, something weird should be happening. Every function has an implied domain. That's the first little thing we need to know. Now let's go to, let me give you one more. Let me give you another implied domain function. Look at this function. We're going to go back. We're going to go back to pre-cal. What's the implied domain of that? You say 1? What do you mean by that? Not sure. Oh, I think what you're doing is you're taking tangent of some angle. I'm saying what values of x can you or can you not plug into this? So maybe I can help. What is tangent by definition? Sine over cosine, right? That's the definition of tangent. And now you have a fraction, don't you? And that fraction has problems when the denominator is 0, right? So now what you need to ask yourself is at what angles is cosine 0? So I would go to my unit circle. And what I would do is I'd ask myself, at what angles is cosine 0, which means at what angles is the x-coordinate 0? Where is it? Is the x-coordinate 0? At what angles is the x-coordinate 0? Where? Right here and right here. Right? Because if you look at these ordered pairs, this is 0, 1. This is 0, -1. Cosine is always the x-coordinate. And so the problem would be if this was ever 0. So I'm asking myself, where is cosine 0? Here and here, right? What are those angles? I heard 90 and 270. But go back to pre-cal. There are an infinite number of answers, right? Aren't there an infinite number of answers here? I mean, not just 90 and 270. You could come back around, couldn't you? So I'm now going to get the general solution to this equation. So let me kind of write this out. I want to make sure that cosine of x is not 0, right? That's what I want to make sure, that this is never 0. Well, where does that happen? It happens when my angle is, I'm going to do radians. That angle is pi over 2, right? And then how could I get from that angle down here? What would I have to add to the pi over 2 to get down here? Another half rotation, which is pi, right? And then to get back to here, another pi. And then back to here, another pi. So here's what I want. In order for this to not be true, or in order to avoid that being 0, I need to make sure that x is not equal to, x is our angle, is not equal to pi over 2, that's this angle here, plus pi k or n, depending on your pre-cal class. They might have used a k here or an n. So I know some of you are going to look at this and like freak out right now. So if you are freaking out, it's okay. Get with me on this later. This is a trigonometric equation I'm solving. I'm trying to get a general solution. So that's what I've just done. I said, okay, cosine is going to be 0 here, and then any half rotation multiple will always drop me off at either the top or the bottom. So that's my implied domain. I can plug any x I want into this except these. Every function has an implied domain. I'll give you one more. It won't take us long. What about this function? F of x is x squared. Are there any problems with this function? Do we have any fractions like division by 0? Any square roots of negative numbers? No? You can plug any number you want into this, right? So what's the implied domain? Everything, all real numbers, right? And there's a couple of ways to say that. We can say negative infinity to infinity. We could also write double struck capital R. That means all real numbers, right? That's your implied domain. Okay. So now that we've kind of revisited the idea that every function out there has some implied domain to it, now we get the direct substitution property. Super, super nice property. Remember, our goal here is limits, right? We're talking about limits. This says, if the function you're looking at, f, is a polynomial function, we studied those when? Polynomials were in what class? college algebra. Rational functions, that's the one with like vertical asymptotes, horizontal asymptotes, slant asymptotes, college algebra. Trig functions, we studied those in pre-cal, right? Exponential functions, studied those in college algebra. Logarithmic functions, studied those in college algebra. So pretty much every function you've studied, right? If your function f is any of those, then as long as the a that you're approaching in the limit, as long as that a is in the implied domain of the function, then in order to find the limit, all you have to do is plug the value of a into the function and you're done. So let me show you an example of what this property is saying. Let's say I'm trying to find the limit as x approaches 4 of x squared plus 1 over x minus 3. I would like to know what happens on this graph, right? If you were to graph this function, what happens is you approach 4 from both sides. No pictures. I'm not giving you a picture, right? I want to know what happens, though. So you look at this and you say, all right, see that function, f? Think about its implied domain. What's the one number you cannot plug in? 3. Where are we approaching? 4. 4 is in the implied domain, right? The only number we can't go to is 3, right? So 4 is in the implied domain. So according to the direct substitution property, all I'm going to do is take this function and replace every x I see with 4. And my answer would be 17 over 1, which is 17, I believe. I did that fast. 16 plus 1, right? What am I doing? I'm doing a direct substitution of 4 into the function. That's my answer. Now, if you don't believe it, I can at least try and convince you visually. Let me hide some of this. I'm going to have Desmos graph this. X squared plus 1 over x minus 3. There's the graph. I'm going to close this just because I get a glare off the board and it messes up my video. All right, so there's the graph of that function, crazy looking graph. And where were we approaching? 4. So I'm going to kind of bring this down like this. We're approaching 4. Let me draw a vertical line. And I'll make it dotted, make it orange. So we're approaching 4, right? We're approaching 4 from both sides. So we're coming in along here, right? And then we're also coming in from the left. And where are we approaching? This point right here, right? And what is that value? 17. See, whenever the number we're going to, well, it's not here, I erased it. Whenever the number we're going to is in the domain, then all we're doing is just plugging the number in, which is super nice, right? Wouldn't that be nice if this was all what calculus was? You just plug in the number and it's nothing crazy. All right, so that's the direct substitution property. Unfortunately, direct substitution is not what we're interested in. We are interested in problems where the function has the implied domain and we're approaching something that's not in the domain. That's what we want to be looking at in this class. So here's our first few examples. We're going to work through these. Normally in my lecture notes, if it's in orange, it's an example I'm going to do on the board. All right, so we look at this. I want to know what happens as x approaches 1 from both sides of that, and I'm not graphing it. The first thing I'm going to do is try direct substitution. I'm just going to try and plug 1 in and hope that it all works out to a nice number. So let's try it. What happens if I do direct substitution? 1 squared plus 1 plus 2 over 1 plus 1. Hey, this is looking good. On top I get 4, on the bottom I get 2, and my answer is 2. And that's it, I'm done. Direct substitution worked there because there was no problems here, right? 1 was in the implied domain. What would have been a bad number to go to? -1 would have been a bad thing, right? Okay, first example, direct substitution, everything's beautiful. Questions? Now things start to, the wheels start to come off a little bit now. Always try direct substitution first. If there's a problem, you're going to see it. All right, we're about to see a problem here. Let's try our direct substitution. I'm going to put an arrow because I know there's going to be a problem. What happens on top is I get 1 cubed minus 1. And on the bottom, I get 1 minus 1. So what's my numerator? 0 on top, and on the bottom? 0. And 0 over 0 is undefined, right? This was the heart of the calculus, though, right? That's what I told you. This is what Newton was trying to figure out, is there a way around this, right? So right now, we're getting 0 divided by 0. Take out that sheet of paper that I handed out to you today that was just the single sheet. The limit summary. Are there any extras laying around? Do I have them? No. There's a few over there. Thank you. Thank you, thank you. All right, this right here, this sheet with the boxes is what I call the limit summary. Feel free to write that on the top if you want. Limit summary. And I want you to look at the top left box. And what you're going to see in there is 0 over 0. Do you see that? And then a bunch of other crap. Do you see all that other stuff there? You see the 0 over 0. Do you see that we are taking a limit and we are getting 0 over 0? Right? This is one scenario that could happen when it comes to limits. Everything else on this box, in these boxes, is all these other scenarios that we're going to have to investigate over the next few days in this class, right? So when you see 0 over 0, what does it say that we need to do? Below that, at the very bottom of that little box, it says what? Use algebra or some trick. So anytime we see 0 over 0, we now need to break out the algebra tools or some tricks. I mean, you'll see what I mean by tricks later. So I like to tell my calculus students that when you see 0 over 0, I want you to be thinking that this is bad, all right? This is bad. This is bad, all right? We have to find a way around this. And according to this chart, we're going to need some algebra or some trick to do it. So I'm going to come back over here. I'm going to rewrite this limit. And now it's time to break out the algebra. So I look at this expression here, this function, and I think about all the algebra that I've learned. And I go, wait a minute, I remember this thing where we had right here a difference of cubes. It was in college algebra. There was this thing called difference of cubes. Y'all remember that? There's a formula. It's on one of your sheets. Here's what it says. If you have x cubed minus y cubed, this is equal to x minus y times x squared plus xy plus y squared. That is your difference of cubes formula from college algebra. It's kind of like that. You're thinking of the binomial expansion thing. Do y'all see it? Do y'all find it? What page is it on? First page, right? First page. It's the one that says factoring special polynomials. It's hard to see that, isn't it? X cubed minus y cubed. I'm going to use that formula. For us, we have x cubed minus 1, right? So we have, this really looks like for us, it's like x cubed minus 1 cubed, right? We could rewrite this 1 as a 1 cubed. And then we could see that it's x cubed minus 1 cubed. And so the 1 is the y, right? The 1 is like the y. Do y'all see it? So what does it become according to this formula? X minus 1 times x squared plus x times 1, which is x, plus 1 squared, which is 1. That's the way the numerator factors, right? So I'm going to come over here and I'm going to rewrite this. Watch. I'm going to rewrite limit x approaches 1. See how I actually wrote the limit a second time? Like I'm saying this is equal to this. I'm keeping the limit there because all I'm doing on this step is just algebraically rewriting the numerator. That's all I'm doing. So I keep it there. Now I put this on top. X minus 1 times x squared plus x plus 1. All of that over 1 minus x. Any questions? Like I said, it's the algebra that starts to become the villain in the room, right? Because it's how much algebra, how comfortable are you with it? Do you see it? You know, do you recognize what to do? Now what? I mean, I did that, right? That's some algebra, but what I'm trying to achieve, before I lose focus on things, what I'm trying to overcome is the division by 0. I'm trying to overcome that. And so to overcome that, I somehow need to see if there's a way that I can get this to kind of go away. And by factoring the numerator, right, I see that this and this are almost the same, right? They're almost the same. They're not exactly the same. This is x take away 1. This is 1 take away x. They differ by how much? By a negative sign, right? So what I'm going to do now is I'm going to factor a negative out of one of them, and it's kind of my choice. Let me erase this. I'm going to move this down because there's this scratch on the board that gets in my way. Limit, I'm rewriting the limit, right? X is approaching 1. I'm going to leave the numerator completely alone. And on the bottom, watch, I'm going to factor negative 1 out, and that makes that negative 1 plus x. Do you all agree with that? If I take a negative 1 out of here, then when I distribute that back through, I get positive 1 and then minus x, which is this exactly. But why have I done that? This is that, right? I just have to switch the order. So I could say, no, instead of that, I could just make that x minus 1, right? And then my negative 1 in front. So I factor the negative 1 out, just kind of flip those around. Now they will cancel out, right? Okay, I need to hit the pause button real quick. I hate to hit pause right now, but I'm going to. That's pause, okay? I have a question for you before we finish this problem. Just this, I just need this much space. I'm going to give you two functions right now. And my question to you is whether or not these functions are the same functions. Do they draw the exact same thing or not? Think about it. We'll take a vote. Are y'all too scared to vote if I ask you to vote? Are y'all going to vote? Is everyone going to vote? Everyone's going to vote. All right. So how many of you think that these are the exact same functions? Okay. How many of you think they are not the exact same functions? Well, we've got a split. Okay, so for those of you who think they're not the same, can somebody volunteer to explain why you think that? Go ahead. What's your name?
David.
David. Okay, what do you think, David? Why are they not the same?
If you have 0 over 0 replaced for x over x, then it won't be.
So I think what David's saying is that if I ask you for g of 0 over here, right, you're going to try and do 0 over 0, which is going to be undefined. And over here, if you plug in 0, what does it spit out? 1, right? Just 1. So it's like these aren't giving you the same values, are they? I understand David's argument. Now, for those of you who think they are the same, does someone want to counter David's argument? Any other number would work, right? So let's say I plug in 2 here. What would I get if I plug in 2? 1. And that would be 1 as well, right? If I plug in 5, I get 5 over 5, that's 1. And they would be the same. I agree. At every number other than 0, they're the same, right? But I asked, are they the same function? They differ at one value. But hold on, wait a minute. Couldn't we have just started out by just canceling that, turning into 1 to start, and then we don't have the 0 over 0 anymore, do we? Is that an argument? It's an argument, but it's a bad argument, and here's why. Back in college algebra, you're taught you can do that, right? X over x, that's 1. Right? You're taught you can do that. anytime you cancel factors like that and turn it into a 1, there's something that I hope your professor told you that maybe they did, maybe they did, maybe they didn't, maybe they did and you didn't pay attention or didn't hear it, they didn't say it loud enough. When you cancel two factors like this, you have to make me a promise. You know the small print, you know, you read like something that's got small print on the bottom? When you cancel factors, you automatically add a little small print on the bottom that says, so long as x is not 0. So I can cancel these and turn it into a 1 so long as I promise I'm never going to let x be 0, because when x was 0, there actually was a problem there, right? So when you cancel factors, there's always that thing in the bottom that's saying we have to promise that we never let the x be whatever it would be that would make that thing have a problem. Let me give you one more quick little example. What if I replace this with this instead? X plus 2 over x plus 2. Are these two functions the same? No, because this one will have a problem where? At negative 2. Now I can cancel that and turn that into a 1, but now you have to promise me what? That x can never be negative 2. So that means this one will be defined at negative 2, right? But this one won't. So the big takeaway here is I'm about to cancel these factors. You see this? I'm about to cancel these. I'm about to do this. But what are you now promising me? As long as x is not 1, right? So I'm allowed to do this cancellation as long as I promise you that x is not going to be 1, right? So let's continue over here. I'm going to do the limit. X is going to approach 1. On the top I canceled, so I have x squared plus x plus 1. On the bottom, what do I have? Cancel. I still have the negative 1 there, right? Now what am I going to do on my next step? I'm going to let x equal 1 or approach 1. What is the limit really saying? Approaching, right? You see, it's super important that we're using the limit right now because this says I can't let x be 1, right? And I'm about to let x get closer and closer and closer to 1 without ever being 1. But see, at this point, I have a direct substitution property from before that says as long as this number is in the implied domain of that, then I just replace the x's with 1s. So it's kind of a weird thing going on here. You know, we have this limit, we have this problem, we overcome it with some algebra, we make a promise that x can't be 1, but because we're talking about a limit and because there's no longer a problem, we can actually replace the x with 1. It's weird, but that's the way it works, all right? So I'm now going to replace the x with 1, and what happens on top? 1 plus 1 plus 1, we get 3 on top, and on the bottom, negative 1, so our answer is negative 3. When did I stop writing the limit? When did I actually stop writing LIM?